Hello, in this lecture I will go over some examples of equilibrium of a rigid body in three-dimensional. The first example that I have asks us the rod supported by journal bearing at point A and cable BC is subjected to an 80-pound force. Find reactions at thrust bearing A. That should be journal. Bearing A and cable BC. Okay, so step one, same as before, is free body diagram. I'm going to draw FBD of A, D, B. That means I'm going to isolate and draw outline of the shape. Then I'm going to put active forces, the forces that are trying to disrupt the equilibrium. I have one that is 80 pounds. Then I'm going to put reactive forces. I have cable BC, point B. Cables are always in tension, meaning going away from point. So I'm just going to put FBC or TBC. And then I have a journal bearing. So you have to go back to my lecture on supports in 3D format when I talk about journal bearings and stuff. But I'm going to have this little table here. In 3D format, we are going to have X, Y, Z, and MX, MY, MZ. These are indication of forces. These are moments. A journal bearing, it can move in this direction back and forth, and it can rotate. So those two are going to be yes. So that means, can it move in Y direction? Yes. And can it rotate about this axis, which is Y? Still yes. Anything else is a no. Can it move in X direction? No. Can it move in Z direction? No, it's fixed. Can it rotate about X? No, it cannot. It's fixed. Can it rotate about Z this way? No, it cannot. So I'm going to pick the no's and I'm going to draw them. Just to be safe and to start easy, put everything in positive direction. This is X, Y, this is Z. So I'm going to put AX. I have AZ. And then I have moment about X. I'm going to put it in positive direction. M, point AX. I like to put an arrow on top of it to make sure I know it's a moment. And I'm going to use right hand rule. Direction of rotation is where I curl my finger. My thumb is going to be where the moment is pointing. And the next node that I have is moment about Z. So this is M, A about Z axis. I like to put a rotation on it, so I remember that's a moment. Okay, so how many unknowns do I have? I have FBC, AX, AZ, moment of A about X, moment of A about Z. 1, 2, 3, 4, 5 unknowns. Okay, let's start. So for problems that all the forces, all the moments are along the axis XYZ, which is in this case every force, every moment is either in positive axis or negative axis. They're all parallel. It's usually simpler that I just use the format that I'm going to use right now. I'm going to use the same as before. Sigma fx being positive, anything that points with my axis x, I'm going to put positive next to it. Look for all the forces that are in x axis. AX, I see that is AX. AZ, 80 pound, FBC, they're all in Y direction. So that's my first unknown. That's done. Next, let's do a sigma summation of forces in Y direction. If I do in y direction, I have two unknowns, FBC and AZ. Or no, sorry, there's no y. That's why. Okay, I was talking about z. So summation of forces in z direction, anything that's pointing up is going to be positive. AX, I have an AZ, which is plus. I have minus 80 pounds. I have plus FBC equals 0. Okay, and I cannot write sigma Fy because absolutely I do not have any forces in y direction. So that equation is not going to help me. So I'm going to go help from one of my moments equation. Let's see, I can have moment about x, moment about y, moment about z. But let's see, what if I write summation of moments about axis y being 0? Anything that makes this whole free body diagram rotate about axis y. So let's see, AX, it doesn't make it rotate about y. AZ, it doesn't. Moment AX is about axis x, moment AZ is about axis z. But let's look at these two forces. So let me draw it kind of here. This is axis y. I have a force of 80 pounds pointing down. I have a force of BC going up. So to me, that 80 is trying to rotate, make a rotation about axis y. And if I use right hand rule, if I curl my finger where this arrow is pointing, my thumb is going to point to negative y-axis. So it's going to be 80 pounds. The distance that I have for it is 1.5 feet, and that's negative direction. The other force that I have is FBC. FBC is trying to rotate this whole rod with y-axis. If I curl my finger towards where the arrow is, so this way is positive, so that's going to be positive. I have FBC multiplied by the distance is 3 feet, and that's it. Okay, so from here I get FBC of 40 pounds, and if I put it back up here, that will give me A sub Z of also 40 pounds. Okay, so those are my three forces. I still have two unknowns. So I found FBC, I found AX, AZ. I still have two moments to find. Let me draw the free body diagram here really quick. I have FBC, which is 40 pounds. I have this 80 pound going this way. I do not have AX, but I just like to still write it there as 0. I have AX. I have AZ, which I found it to be 40 pounds. And I have MA about the axis. Okay. So let's look at summation of moments about x-axis being 0. Okay. Anything that is trying to rotate my beam about x-axis. AX and that 40 pounds, which was AZ, they're not creating any rotation. But look at these two, the 80 and the 40. This is my beam. This 80 x-axis is trying to rotate this whole thing about x-axis, isn't it? At this distance, which is 6 feet. So my first one is 80 pounds at a distance of 6 feet. Now let's use right hand rule. So if I curl my fingers with this, my thumb is going to point to negative x-axis. So I'm going to put negative there. Okay. The other force that I have, this is x-axis, this is my rod. I have an FBC of, how much was it? 40 pounds. So this FBC is acting at a distance of 6 feet, is trying to rotate this whole thing this way, isn't it? And if I curl my finger that way, direction of moment that is creating is towards x-axis, positive x. So all I have to do is 40 pounds by a distance of 6 feet. And don't forget this, there is a moment, unknown moment existing. So these are the only thing that I have, moments about x-axis. If you do the math, you're going to get the moment of the unknown moment that I'm trying to find, 240 pound-foot. And that's positive, means the way I drew it was correct. And last unknown that I have, let's find summation of moments about z-axis being 0. Anything that is trying to rotate this beam around z-axis, trying to rotate it this way. So any forces that I will have that are on an x direction, or positive or negative, is going to be creating that rotation for me. Anything that pushes the beam this way or pushes the beam this way is going to create a rotation about z, either positive or negative. So, and I don't have any type of those forces. So the only unknown that I have is moment of A about z-axis. There's nothing else that creating that moment. So that moment in its own is 0. This unknown that I wrote is right here. That's where I bring it in. Okay. Let's look at another example. This one is something that I explained in my lecture, how to draw the free body diagram for it. These bearings A, B, and C is what we call properly aligned. And that means they only develop forces, no moment. Okay. So let's see. Free body diagram of the beam ABC. Let me draw the outline of this rod. Okay. Put active forces on there. Okay. One thing I got to do, I like to find, well, let's just draw F for now. I'll get to it. I wanted to do the components of it, but doesn't matter. Okay. Now I have 3 bearings, A, B, and C, that they only have forces. So all I care about is the X, Y, and Z, and see which way they're moving and which way they're not moving. I said journal bearing has the possibility of moving back and forth. So when you look at A, the only way that it can move is Y. Everything else is a no. When you look at B, it can move back and forth this way, which is in X direction. So yes, it can move, no and no. When you look at C, it can go back and forth, and so that means in Z direction, yes. In Y and X is a no. So now everywhere that you see a no, you got to draw a force. Point A, I have an AX and I have an AZ. No moment. Point B, I have a BY and I have a BZ. Point C, I have a CX and CY. And that is my free body diagram. Okay, so let's find the components of this force. F is given 800 newtons. So let's find components of this force. So component of this force, you have to go back to chapter 2 to remember how to do this. Okay, this is where we have the transverse angle. So I'm going to go over it really quick. So x component of it is going to be f cosine 60 multiplied by cosine 30. Remember, this is the shadow. This is f cosine 60. And then if I find cosine 30, that would be x. If I find sine 30, so this is f cosine 60 cosine 30, which is an x. And this one is going to be f cosine 60, the shadow, multiplied by sine 30. And that's going to be y. And z is just f sine 30. Or sorry, f sine 60. Right there. In other words, it's f cosine 30, the angle that it makes with z-axis, which that one is negative. So for me to remember, I'm just going to put negative right there. So the values for each of these is going to be 346.4, 200, and 692.8 newtons, and newtons. Okay. So let me draw the free body diagram one more time, really quick. This is going to be my rod AB, and these are going to be my forces, CX, CY, BZ, BY. F now has 3 components. I'm just going to write it the way I found them. 346.4. Fy is 200. And Fz is 692.8. The last thing I have, point A, is AX and AY. Okay. So to do this one, I am going to start with my 3 equations that I have for forces. So summation of forces in X, summation of forces in Y, summation of forces in Z. Anything that points this way, positive. Anything that points this way, positive. Anything that points up, positive. Look at every force that has a subscript of X. I have AX. I have a CX. I have a 346.4 equals 0. For Fy, anything that points in Y direction or have subscript of Y, 200 plus By plus Cy equals 0. Just put units there. Summation of forces in Z direction, AZ plus BZ minus 692.8 Newton equal 0. Okay, so these are the equations for my forces. Now let's look at the moments. Let's write summation of moments about x-axis. Anything that's trying to rotate this about axis x. Oh, by the way, guys, I corrected that AZ. Should be AZ. Okay. Summation of moments about x-axis. Anything that is trying to rotate this whole beam about x-axis, either this way or this way. So if you look at the figure, CY and AZ are the only two forces. So let me draw them really quick here. CY is trying to rotate this whole thing 2 meters about x-axis. Okay, you see it, this CY is trying to rotate this whole beam about x-axis. So CY, the distance to x-axis is 2 meters, and if I use right hand rule, fingers curl towards this direction, that's pointing towards minus x. Okay, CY is one of them, AZ is the other one. AZ is trying to rotate this whole thing also about x-axis. And so AZ, the distance between AZ and x-axis is also 2 meters. And that one is plus. Or that one is also negative. Oh, they're the same direction. Sorry. Okay, let's think about summation of moments about y-axis. Anything that is trying to rotate this about y-axis. The only two forces that I see are BZ and CX. So let's see, BZ is trying to rotate this whole thing about y-axis with a distance of 1 meters. So B sub Z 1 meters. Use the finger right hand rule and fingers curling. That's going to be plus. And the other force that I see is CX. Right there. CX is also trying to rotate this beam about y-axis. So that's CX multiplied by the distance that is having from y-axis is 2 meters. And that one is same direction, so that is plus, and that is going to be 0. The last one that I have, I don't want to go to the next page, so I'm just going to write it up there because I want to use the figure, is rotation about z-axis. The only two forces that I see trying to rotate is AX. It's trying to create a rotation in this way, and that is positive. So AX, the distance to z-axis is right here, which is 2 meters. And the only, I see two other forces. I see BY also. BY is trying to rotate about z-axis. Sorry, it's pointing down. And if I use my right hand rule, I'm going to have a BY at a distance of 1 meters. And the other force that I see is CY. CY is also trying to rotate this whole thing about z-axis. This force is creating a rotation about z-axis. CY in a distance of 1.75 to z-axis would be 0. So CY, use right hand rule, curling the finger this way. My thumb is going to point down, so that's negative. BY, where did BY go? BY this way, same direction, so that's going to also be negative. So this got a little bit messy, so I'm going to write all of the equations one more time, kind of nice and neat here. AX plus CY, CX plus 346.4 equals 0. Forces in Y, 200 plus BY plus CY equals 0. Summation of forces in Z direction, AZ, BZ, 692.8 equals 0. Summation of moment about X equals 0. minus AZ 2 meters minus CY 2 meters equals 0. Summation of moment about Y plus B sub Z 1 meters plus C sub X 2 meters equals 0. Summation of moment about axis Z is 0. AX 2 meters minus BY 1 meters minus CY 1.75 meters, that will be 0. So any method of solving these equations you want to use, it's totally fine. It's usually better if you start with an equation like this one. Find CY being minus 200 minus BY. So go ahead and anywhere that you find CY, go replace it by that. The other thing is if you can replace AX also from one of those equations by CX or AX, you can replace it by CX. Yeah. So you gotta just kind of substitute and get rid of variables until you have 3 equations, 3 unknowns, or 2 equations, 2 unknowns. And then you can do eliminations, you can do substitution, you can do matrices, whatever you want to do and use, it's fine by me. That is not the subject of this course, so that is why I'm not going to go over it and teach you. So you got to go back to calc and or even high school math and figure out that how to do 3 equations, 3 unknowns, 4 equations, 4 unknowns, and so on. So one of those, let me see, CY, yeah, so C 53.6 and CY of minus 800 newtons is the result. Okay, so let's look at another example, but I'm going to do a little bit of different method here to solve this example. Member AB is supported by a cable BC and at A by a square rod which fits loosely through the square hole in the collar. So let's see, determine the component of reaction at A and tension in the cable needed to hold the rod in equilibrium. Alright, so let's just start with free body diagram. And you know what, I'm going to do free body diagram next page. So let's just start with here. So free body diagram, I'm going to do free body diagram of AB. So let me see. I'm going to go and draw the outline of AB just like that. Then put active forces on there. 200 newtons, 400 newtons, and then reactive forces. Point B, there's a tension, it's a cable, it'll always go away, so it's going to be T. Now point A, square rod, I'm going to have my X, Y, Z, moment X, moment Y, moment Z. Alright, let's go one by one. Does this move in X direction? No. Does this move in Y direction? No, it's fixed. Does it move up and down? Yes. It's a collar with a square hole on a square shaft, so it can go up and down, so it's a yes. So let me put forces right there. These are all forces. So I'm going to have an AX and AY. Okay, AY and AX. Okay. Now let's look at the rotation. Can this rotate about x-axis? Nope, it's fixed. Can it rotate about y-axis going this way? Nope. Can it rotate about z-axis? So in normal cases, if it was a circular rod with a circular hole, it could rotate, or something like a journal bearing. But now it's a square fitted on a square, so it cannot rotate. So it will generate 3 moments for me. So MA about Y using right hand rule, so it's going to rotate this way. A, moment A about Z, and moment, I'm going to draw it back here, moment A about x-axis. So I have 3 forces, AX, AY, and T, and 3 moments. I have 6 unknowns. So I'm going to use a different method here for this problem. For this problem, turn everything into vector format. Okay, so now I'm going to go back here. So turn everything into vector format. Turn everything into vector format. So I'm going to have a force at point A. I'm going to have a force. This one I'm just going to call it F. And we are going to have a tension. Okay, force at A is AX and AY. So it's going to be AXI plus AYJ newtons. Force F, which is active force and it's given, it has a 200 newtons pointing towards positive y-axis. So it's going to be 200J. And it has 400 pointing down. So I'm going to say minus 400K. The other force that I have is force of tension in cable BC, which is going to be tension by unit vector of BC. We're going back to previous chapters. Unit vector of BC is going to be RBC over magnitude of RBC. RBC, I'll go over these really quick, is going to be coordinates of C minus coordinates of B. So it's going to be 0 minus 3I, 1.5 minus 0, J, 0 minus 1, K. Okay, so that's going to be minus 3I, 1.5 J plus K. And position vector BC is going to be 3.5 meters. Okay, so TBC is going to be minus 3 over 3.5 T I, 1.5, 3.5 T J, 1 over 3.5 T K. And the units, I'm assuming it's eventually going to be Newton. So now what we are going to do, we will just use the vector format of equation of equilibrium. Summation of forces in vector format equal 0. So put everything that you see with an I in all together. Minus 6 over 7. I just multiplied by 2, so let's not do that. So let's just stick with what we have. So minus 3 over 3.5 T. F doesn't have any I, plus AX I. Next one, 1.5, 3.5 T, plus I see an AY, plus 200. Anything with a J, I'm just putting it together. And the last one is 3.5 T, AX, AY, I see a 400K, and that's it. Equals 0. So for this equation to be equal to 0, this needs to be 0, this needs to be 0, this needs to be 0. Basically, summation of forces in Z equal to 0, summation of forces in Y, summation of forces in X. I just like to show you a different format of writing it. It's all together. So from the last one, you can figure out that the T equals, let me write it here, T equals 1.4 kilonewtons. Okay, I changed units on it. And then you put it in the first one, you get AX of 1.2 kilonewton, and then you put it in the last one and you get of AY of 800 newtons. Okay, so that was in forms of vector format. The other thing that I want to do, let's take summation of moments in vector form about point A equals 0. Okay. So for this one, I have to write everything in vector format. I have moment AX, okay, which is I. Sorry, it doesn't need vector. Plus moment of A Y J plus moment of A Z K. So these are my three unknowns that I've already put at point A. AX, AY, they don't generate any moment. Then I have the force F generates a moment at point A for me, plus I have, so let's call this R1. R2 multiplied by T generates a moment about point A. So I am finding moment of this force F, which was 200J minus 400K, and moment of this T about point A. So let's just quickly look at the position vectors and what each R is. This R, if you remember from moment chapter, is from point to line of action of force F. So R1, if you want to look at R1, it's going to be from point O to line of action of force, which is right here. This is my R1, which you can see it is 3I 0J 0K meters. R2 is from point A to line of action of T. Line of action of T could be this point, okay, or could be point C. This point C is on the line of action. So it's much easier if I just take this one as R2 from point O to line of action of force, which is also point 2, because it's much easier for me to find it. R2 is just 1.5 J meters. Okay, and sorry, I forgot to put the arrow here. So I have T, I have F. Let me write it in the next page. So M A X I plus M A Y J plus M A Z K plus, I'm doing R cross F, so I need IJK in there. The R1, which was 300 meters, and F, which was 200 minus 400 newtons, plus R2, I'm doing IJK again. IJK, this is a vector, 0, 1.50 meters, and T, if I find components of T, is going to be 400 newtons. All of this equals 0. So if you do the math, you are going to get something like this. MAX plus 600 I, MAY plus 1200 J plus MAZ plus 1800 plus 600 K equals 0. So look, summation of moment about x-axis, summation of moment about y-axis, summation of moment about z-axis equals 0. Simple enough. So that means this should be 0. So max is minus 600 Newton meters. may is minus 1200 Newton meters. And maz equals minus 2400 Newton and meters. So this is just to show you a different way of solving it. I have another example just like this one for you to figure it out. So I'm going to go through this one much quicker. Okay, so the bar AB has fixed support at A. Fixed support, no movement in any direction, no rotation in any direction. So that means when I do the table for fixed support, X, Y, Z, M, 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 X, Y, Z, they're all going to be no, 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 no. So draw free body diagram of the bar. Reaction at point A, support can sustain this much. Okay, so let's go through one by one. Let's draw free body diagram of the bar. So FBD of bar AB. Do not include anything else on there, right? There is no active force, but there's a tension here. So that is active force here, which is T. And then I have a force in every direction and a moment in every direction. So I'm going to have AX, AZ, AY, MX, MZ, and MY. So I have 7 unknowns. Oh, I don't, because the magnitude of T is given. Okay, good. So I have the 6 unknowns. So let's find the components of T. So let's do the vector format here, okay? So I have, let's transfer everything into vector format. F A is just going to be AXI, AYJ, AZK. T is going to be 300 unit vector of BC. I'm going to skip the steps for it because I just explained it in the previous problem. So that is going to be 93.7 I, 218 J, 46.8 K, and it's going to be pounds. Okay. With that, let's write summation of forces in vector format equals 0. So that means AX plus 93.7 I equal plus AY minus 2811 J plus AZ 46.8 K equals 0. That means this needs to be 0, so AX is minus 93.7 pounds. This needs to be 0, so AY is 281.1 pounds. And AZ is going to be minus 46.8 pounds. So those are my 3 forces. I still have the 3 moments. So if I want to do the same thing as problem that I did before, summation of moment, let's take it about point A being 0. I have MX, I, MY, J, MZ, K, plus R cross T equals 0. Moment of T about point A. Okay. This R could be AB, could be AC, because it's from the point to line of action of the force. I took it from point AB. So it's going to be MXI, MYJ, mzk plus I j k, position vector from A to B is going to be 6, 6, 2, and the T, I just found it on the previous slide, and it's going to be 281.1 and 46.8. This is pound, this is feet, equals 0. So if you do the math, you're going to get mx of minus 843 pound foot, my of 93.7 pound foot, and mz of 225 pound foot. Okay, the last part of the problem, I want to go back. If support A can sustain this much torque or moment. Torque and moment are a little bit different, but this is what it says. Does the tension of 300 pound in row PC, which we have, cause failure at A? So let's see. So this is just like a vector. So I have vector moment about A equals minus 843 I 93.7 J plus 225 K pound foot. So it's a vector. The magnitude of the vector, just same as before, is the square of the component square root of that, which is going to be 2405 foot pound. So that is the how big the reaction at point A is. This is how big the moment point A is because we put a tension on it. The problem says it can sustain up to 3000. So the answer is no failure, and this rod will hold perfectly fine with that much tension that we put on it. Thank you.